In this video, we're going to think about transformations we can apply to our variables in order to improve the linear models. So the situation we're going to imagine is that we've tried a basic linear model of the form y equals a plus bx plus epsilon or something like that, so just a linear combination of parameters. And we look at our diagnostic plots and we find that the model we've used is inappropriate. Okay. The question is, what can we do about this? How can we fix the problem we found by looking at diagnostic plots? Well, the first thing we can try is adding other covariates into the model if they're available. Okay, so instead of just having y regress on x, we could also regress it on x and u and v, etc. if we have information on other quantities, u and v in this case. So, for example, if y was predicting salary, okay, and x was the age of employees, then we might find that saying salary is a linear combination of your age to be an inappropriate model. Okay. But if we had information in on gender, okay, or region that you live in the country, then that might improve the model. Of course, in many situations that's going to be inappropriate solution in that we won't have additional covariates. We'll have included all the covariates we have already into the model. What can we do in this situation? So one thing we can try is transforming the variables that we do have. So in fact, instead of fitting y is a plus bx, we could try transforming the x variables, for example. So we could try y is a plus b times log x plus an error 2. Okay, where instead of using x, we've used log x. Now note that this is still a linear model. Okay? A linear model is a model that is linear in its dependence upon the parameters a and b. Okay? So here we've got y is a plus b times log x. So it's linear in a and b. So it's still a linear model. And if x is negative here, we can do something like take log of x plus a constant, say, where the constant is such that x plus c is always positive. Or we can add additional terms. Okay? So we've got y is a plus bx plus cx squared. Okay? So we've included x twice in a sense. We've got x and x squared, but that's okay. We'll just fit a quadratic equation to the data. And we can continue further. We could have plus dx cubed, plus an x to the fourth term, and so on. Or add a log x as well, or a square root of x. And you can try all kinds of weird wonderful combinations. We have to be careful doing this to avoid what is called overfitting the model, and we'll talk about that in the next video. But we can, in principle, have many different transformations of x in there. The other option is to try transforming the y variables. So, for example, log of y is a plus bx plus an error 2. And this, of course, is equivalent to fitting the model y is e to the power a plus bx plus epsilon. Okay. And notice again that it's still a linear model because a and b are only there in linear combinations. So how do we choose which transformations to try? Finding a good model is a case of trial and error to some extent. We're going to try out multiple different transformations and see which ones work best. But there is some guidance that can help. One thing that is particularly useful is this diagram on the left here. This is called Mostella and Tukey's bulging rule, and it gives you general advice about what kind of transformations you can use when you see the pattern shown here. So for example, if you see a pattern like shown in this top right corner, which curves around like this upper right quadrant of a circle, okay, what this diagram tells you is that you can try transforming y to y squared or y cubed, okay? Or you can try transforming x to x squared or x cubed. Okay? And similarly, if you see a pattern like this, curving this way round, you could still try x squared or x cubed, but now you might try log y or square root of y. So let's suppose we're given data x and y up here. So what I've got here is just a scatter plot. Okay, it's always a good idea to produce scatter plots of your data. Okay. And I fit the line y equals a plus bx to it. Here we have estimated a and b, and that's the red line. Okay. And we can see, although this is reasonable, it's catching something about the relationship between x and y. Okay. It doesn't look perfect. Okay. It looks like there's some curvature here that we're missing with our model. So how could we correct for this? Well, you can probably guess in this case what to do. But if we go over to Mostello and Tukey's bulging rule, we can see that we could try adding an x squared or an x cubed to the model. Okay. So if we do that, this is what I've got here. Okay. If we do that, we get a much better fit. So this line here is the line y is a plus bx plus cx squared. Okay. And this, we can see, fits the data much better, and it's still a linear model, and so we can use all our theory about how to fit linear models. Just one word of warning about transformations. Generally, if you're going to add additional terms, for example a quadratic term in x to your model, so an x squared term, you must still keep your linear term. Okay? So it wouldn't make sense to have a model of the form of this form. This would not be a good model, a plus cx squared. Okay? We still need the linear term in there to capture the linear part of the dependence. Let's now look at a different example. Okay, so I've got a different set of data here. I've got a scatter plot on the left, I've got y versus x again. And again, I fit the model y equals a plus bx plus epsilon here, and that's the red line. Okay, and that looks okay. So that line is clearly capturing the most part of the dependence between y and x. But you can kind of see it from this plot, from the scatter plot, that the variance of the errors looks to be getting bigger. Okay, so there's a bigger spread between the errors, the distance from the line and from the points to the line over on the right here than there is down here, where the fit is better and the points are closer to the line. If we look at the residual plot, this confirms this. Okay, so we can see this is the residual plot in the middle. We can see what's called a right opening megaphone shape here, that the variance of the residuals is quite small and the fitted values are small. So fitted value is about 2, so that's down here. We see quite a small variance. But the large fitted values up at 11, okay, we can see quite a large variance. Okay, so for values out here, we see a large variance. And again, if we look at the QQ plot, we see again that the normal distribution looks to be violated. We've got heavy tails here. So what's happening here? Okay, we've violated the variance of epsilon I is not constant. That is the problem. We've got what are called homoscedastic errors. Oh, sorry, we've got what are called heteroscedastic errors. Non-constant variance. Okay, so how can we fit this? Well, the normal way, the best way of fitting heteroscedastic errors, so non-constant variance, is to take the log or some other transformation of the y variable. Okay. So if instead we fit the model log y is a plus bx plus an error, okay, we get the residual plots and the diagnostic plots that are shown here. Okay, so this is the residual plot. You can now see that we've got what is roughly a null plot. Okay, there's no relationship between y and x here. It looks like there's just a random pattern between the residuals and the fitted values. So that's good. And again, the QQ plot also looks to have been corrected. Okay? There's no heavy tails anymore like there were up here. So for any given problem, it's possible to try a variety of transformations to get a good model. So transforming the x variables, the covariates, and transforming the y variable, the response. In general, the scatter plots, like we have up on the left here, are only useful for one-dimensional problems, where you have a one-dimensional x variable, or simple linear regression problems. For multiple linear regression problems, where you have several covariates, typically we want to use these residual plots, or the QQ plots, because they work with the residuals and the fitted values, which are again one-dimensional quantities. So they work in multiple linear regression cases. Remember, when we're looking for good transformations and good models, these plots will never be perfect, and they don't need to be perfect. We're only looking to avoid gross errors, so wild model misspecifications. We're looking for an adequate fit and adequate plots, not perfect plots. So in this video, we've looked at using visual aids to choose good models. In the next video, we're going to look at statistical ways to judge the quality of a statistical model and choose between models.